Hi everyone. In this video, I am going to explain about the electronic admittance in reflex klystron oscillator. So through this electronic admittance, we can calculate what is the amount of admittance appear at the output of reflex klystron due to the applied voltage and the generated current. And as well as we can also find out what are the different types of oscillating modes and what is the condition for the oscillations in the reflex klystron oscillator. So before going into that condition, let us see what is the current flowing through the reflex klystron when a voltage is applied. So we know that there are two types of voltage applied. One is the accelerating voltage, another one is the repellor voltage. Accelerating voltage is used to energize the electron gun, and a repellor voltage is used to repel the electrons that are coming in the repeller space. Okay, so the current, induced current that is I2 is equal to 2 I naught beta I J1 of x dash into, we are writing the current, voltage, everything in the phasor notation, phasor form. So that's why the angle should also be included. It is e power minus j theta naught dash. So take this equation as 1. This is the current produced because of the application of repellor voltage and accelerating voltages. That is I2 is equal to 2 I naught beta I into j1 of x dash e power minus j theta naught. Okay, so I naught is the where I naught is nothing but current produced due to V naught. V naught is nothing but accelerating voltage, or we can say anode voltage. This is I naught, and beta I is nothing but coupling coefficient, or we can say beam coefficient, beam coupling coefficient. So beam coupling coefficient, and e power minus j theta naught dash is nothing but represents phasor form, phasor notation. Okay, so now induced voltage from this reflex klystron, induced voltage is V2 is equal to V1 into e power minus j pi by 2, e power minus j pi by 2. This e power minus j pi by 2 represents the retardation phase of the reflex klystron or reflex cavities. So retardation or delay phase of the cavities, phase of the cavity. So take this equation as second. Now electronic admittance, admittance is nothing but we know that it is current by voltage. So electronic admittance YE is equal to current by voltage, which is nothing but now we have output current or induced current I2 and the induced voltage V2. So the current generated, that is I2 divided by the induced voltage V2. Okay, now after substituting these two and we are writing the V1 in terms of V0, now it is I0 by V0, it is the ratio I0 by V0 into beta I square divided by 2 into theta naught dash 2 into J1 of x dash divided by x dash e power j into pi by 2 minus theta naught dash. Okay, so now before going into the condition for the oscillations, Now let us consider the equivalent circuit. The equivalent circuit for the reflex klystron is as shown in this figure. So we are taking three conductances in parallel along with the lumped parameters capacitor and as well as inductance. So the lumped parameters indicating the capacitance and inductance which are a lead capacitance or stay capacitance and lead inductance or any other wiring inductive components. Okay, all these are lumped parameters that are distributed parameters that are available at the reflex klystrons. Lumped parameters, and these three are denoting GL, nothing but load conductance. GL is nothing but load conductance, and it is GB. GB represents beam conductance, and this one is GC represents copper loss in this reflex klystron. Okay, now the output voltage, which is nothing but output voltage, is V2 for this one, and the current flowing in this direction, it is minus beta E into I2. This minus beta E represents the coupling coefficient of this electronic admittance, and as well as this I2 is the current that is passing through this circuit due to the current, due to the voltage V2. Okay, now let us see the total conductance. See here, GB and GL, these three are in parallel, so we can write G is equal to GC plus GB plus GL, nothing but it is the addition of these three conductances, which is the total conductance. So we can write it as a shunt resistance, in terms of shunt resistance, as 1 upon the RSH, 1 by RSH, which is the shunt resistance. Of this equivalent circuit, Okay, so now what could be the condition for this oscillations? So condition for reflex klystron to oscillate, is minus GE greater than or equal to G. Minus GE greater than or equal to G. What do you mean by G? G refers to the total conductance, and GE, what do you mean by GE? GE where GE is nothing but negative real part of electronic admittance, and this is G refers to the total conductance. So the negative real part of this electronic admittance GE must be greater than or equal to G in order to have the oscillations to be generated in the reflex klystron oscillator. Okay, so using this condition, if we are writing the electronic admittance YE is equal to GE plus J into BE. GE plus J into BE. Okay, so BE is nothing but where BE. What do you mean by BE? GE already we know the real part of this even real part of the total conductance of this reflex klystron equivalent circuit, and BE is nothing but a phase constant. Phase constant, you can write it as BE or beta E, no problem. Phase constant with respect to the electronic admittance. With respect to electronic admittance. Okay, since the electronic admittance is shown as the phasor form in this equation 3, see here. See, this is the equation 3 we are taking. Okay, in this equation 3 we have shown this electronic admittance in the form of phasor representation. E power is nothing but here it shows the some phase value. Some phase value. So we have to show that in a polar representation so that we can identify the condition for which the oscillations are to be generated. Okay, see here we have taken a polar representation of this admittance for the condition where the electronic admittance is having the oscillating modes and as well as the non-oscillating region. See here, the graph, the polar representation of this spiral graph has been drawn between the negative real part of this conductance and with respect to the J into beta E or BE, J into BE, phase constant. Now the spiral of this one where it is a N represents the 2 3 by 4, 1 3 by 4, 3 by 4, 0, and again on the right hand side it is 1 by 4, 1 by 1, 1 by 4, 2, 1 by 4. All these represents, N represents mode number in reflex klystron. Mode number in reflex klystron. Okay, and on this y-axis you are having just real number of this one, N is equal to 1, 2, 3, where you are having that spiral form touches this on the y-axis. Again on the x-axis where the spiral graph touches this, at that particular place we are having N is equal to 1 1 by 1 1 by 4, 0 1 by 4, 2 1 by 4, and so on. Nothing but it represents the mode. Okay, now at this particular line where the dotted line shown, left hand side of this dotted line which represents the theta naught dash, that gives oscillation region, and right hand side of this one that gives a non-oscillation region. That means the condition for the oscillations to be generated, which should be theta naught less than this, it should be in this region. It should be in this particular region for the oscillations to be made. And if it is the right hand side of this dotted line, there is no oscillations. Okay, so finally we can say that the condition for this theta, so the condition for the oscillations is theta naught dash is equal to n minus 1 by 4 into 2 pi, n minus 1 by 4 into 2 pi. So this n minus 1 by 4 we can write it as a number, mode number into 2 pi. This is theta naught dash. This is the condition for which the oscillations to be made. Okay, so in this way we can calculate the we can find out the expression for the electronic admittance and the condition for the oscillations.